Silicon photonics is the marriage of optics and electronics, leveraging years of work in silicon semiconductors to create photonic integrated circuits. Professor Graham Reed is a pioneer in this field. In 1989, he founded the Silicon Photonics Group at the University of Surrey. And in 2012, Professor Reed brought his team to the University of Southampton as the Deputy Director of the Optoelectronics Research Center. His group was the first to publish the design of a depletion mode silicon modulator, which is now an industry standard. Today, he also serves as the director of the Cornerstone Photonics Innovation Center, an open-source, license-free silicon photonics prototyping foundry. In today's Spotlight conversation, Professor Reed discusses the future of silicon photonics and the role Cornerstone can play in its advancement in the UK and around the world.
This is Spotlight from All Things Photonics, featuring intimate sit-down conversations with preeminent figures in our industry. Unscripted, timely, and topical, this series shines the spotlight on industry-leading changemakers from all corners of the photonics landscape, from the gateways of progress to the most impactful challenges of our time.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
Today's episode is also brought to you by American Elements, the world's leading manufacturer of engineered and advanced materials. With a catalog of over 35,000 products available in both industrial bulk and laboratory quantities. To learn more, visit AmericanElements.com. American Elements. Now invent.
Joining me today is Professor Graham Reed, Director of Optoelectronics Research Center at the University of Southampton, and certainly a pioneer in silicon photonics. Professor Reed, thank you so much for giving us the time.
My pleasure. Nice to see you.
Thank you. And Professor Reed, for more than 35 years, you've worked with silicon photonics, and your expertise is now being put to use at the Cornerstone Photonics Innovation Center. Tell me about Cornerstone and its mission for silicon photonics.
Okay, well, Cornerstone is quite an interesting story. We started it because at the University of Southampton, we have, for academia, particularly good fabrication facilities. So we started Cornerstone really just opening up those facilities for other academics in the UK. They could perhaps prototype something, try out their wacky ideas, whatever it was. But it's sort of got a life of its own. And we didn't really advertise it particularly hard, certainly outside of the academic community. But gradually, we started to get industry users. And last year, we actually had more industry users than academic users. We now have sent over 800 shipments to customers, now in 24 countries. And we've been invited into things like Europractice, which is a brokerage system, along with some of the really big foundries and so on. So it sort of grew organically, and then recently we've started this thing called the Photonics Innovation Center.
And now, talk to me about why it is so important to develop a pipeline for silicon photonics in the UK.
Well, there are many reasons, really. I think that perhaps the most important one is that the UK has recently identified semiconductors as a critical technology for UK. And like many countries around the world, there have been supply chain discussions and so on. But perhaps even more importantly, my feeling is that there are so many opportunities in silicon photonics now. There's really still the main single commercial application in data center communications, but riding on the success of that commercial application, I think there are a huge number now of other opportunities. And in particular, for a country like the UK, those opportunities are important because there isn't really any incumbent global leader in a lot of those technologies. So, genuine opportunities exist for smaller companies to make their mark and grow. And I mean, in addition to all of that, of course, the success of silicon photonics has meant that there is much greater demand for the technology. There's much greater demand for people. There's much greater demand for prototyping, and all the good things that Cornerstone can help provide.
And what do you think are the technologies and applications that are really driving up that demand?
Well, there are many. There's applications in healthcare. There's applications in what you might call homeland security because of the ability to detect drugs. Quantum is a big driver. Imaging in various forms. I mean, the list goes on and on. And as I say, a lot of those technologies are emerging still. And there's quite a lot of development to be done in some of them. You might not even have the conventional silicon photonics waveguiding platforms, for example. Work needs to be done to produce and develop new waveguiding platforms, just simply because some of the applications demand different wavelengths, and so you need different technology to support those wavelengths. So it's a really interesting time for silicon photonics in that regard. But on top of all of that, the big communications drivers, so as I mentioned, the main communications drivers have been in data centers, but actually other areas of telecoms is also becoming interesting for silicon photonics. And the whole technology of integrating photonics with electronics. So, sort of known as co-packaged optics, really, for to enhance data center communications predominantly and the demand for data. But inevitably, there will be other advantages and applications that emerge for that as well.
And how can Cornerstone help move these technologies and these new advancements from the research lab and into the industries?
Well, at Cornerstone, we've always tried to sort of help the users where we can with training. So, we've had customers, for example, who are not really silicon photonics people. They might have come from different backgrounds, but they know that potentially silicon photonics can help their application. So we've tried to support them in a sort of ad hoc way as best we can as the Foundry service developed. Now, we also have a very big research group at Southampton. So the Silicon Photonics research group at Southampton is about 70 people. And so it means we can pull people in to perhaps do a bit of consultancy for Cornerstone customers or give them guidance or maybe training, that type of thing. But as I say, we've done this really in a rather ad hoc way. But now that we have the Cornerstone Photonics Innovation Center, you mentioned at the beginning, it's relatively new. We're about a year in. But that has much more of a formal focus to accelerating the journey of startups. So we have startup accelerators involved. We have people bringing training involved. We have lots of networking opportunities. We will have an online portal for everyone to put their profiles up, find collaborators, find people to work with, and so on. So in addition to doing the sort of core Foundry work, Cornerstone will facilitate all of the above. And we even have funding to give out to essentially UK partners, because obviously this is UK taxpayers' money. But it doesn't mean international users can't be part of the Photonics Innovation Center. It just means they're not eligible for that particular funding. So the aim really is to support startups in their journey and accelerate their journey to commercialization over and above doing all of the Foundry work. But there is actually one thing I should mention about the Foundry work. So we are completely open source. So in other words, we don't encumber the IP and we don't lock people in. And so I think this is probably why we've become attractive to startups, because a lot of the feedback we've had is that for startups, often you can't even get into a bigger foundry because they don't really have the volumes a bigger foundry is looking for. But also, quite often, they're not really sure which foundry works for their technology because they're not far enough along the road. So in a completely flexible way, we can help to develop their prototypes so that when they're a bit further down the road, they can make an informed choice on which foundry works for them, before they sort of get locked in or it's difficult for them to change foundries, that type of thing. So I think we offer that kind of flexibility over and above all of the above that I've mentioned.
And it sounds too like there's a nice union there of kind of academia and business, and two things that don't always butt heads, but when they can kind of merge and work together, it sounds like you can create something special at Cornerstone.
Yeah, I'm glad you pointed that out, and that I think is true. When we went into when we wrote the grant application for the new program, we had 108 partners who were essentially contributing in one way or another. And that sort of tells you that the community is backing it. And a lot of those people were industry folks who had either used Cornerstone or had heard on the grapevine that it might be useful for them. So it is working out that way, and I really hope and expect it will continue to. So far, so good. We seem to be making progress, but I think there's so much we can still help people do and contribute to.
That's great. Well, it's the early stages and still developing, so we'll be excited to see how that continues. Um, I want to talk a little bit too about your focuses and some of your work because well known for silicon optical modulators. Talk to me about how that technology has evolved and how pivotal it is in areas like data transmission.
Sure. Yeah. It's absolutely critical. Is the answer to the second question. Because if you want to transmit data, you have to have some means of encoding that data onto the optical signal. And so, there are other forms of optical modulators, but the application in data is really evolved to be a high volume, low cost type, or high-ish volume anyway, perhaps, low cost application area. So a technology was needed that was potentially low cost. And of course, we know from silicon electronics that high volume manufacture can create low cost. Now, in terms of the evolution of modulators, well, it's changed beyond all recognition. I mean, we started working on modulators pretty much from the beginning of me forming the group. I formed the group in '89. I think we published our first modulator paper in '93. So we were probably working on it for maybe a couple of years before that. And so, we weren't even thinking of communications in those days. We were thinking of modulators being part of an interrogation system and a communication system for sensors. So speed was not important. But back in the day, we were probably working at about 20 megahertz. Now we have produced a modulator that will go over 300 gigabit per second. And the demands of industry in the next sort of about 18 months or so are to have 400 gigabit per second in a single channel. Now, some people will tell you that means that silicon modulators, silicon-based modulators in silicon photonics are starting to reach their limits. And that's why you're seeing other materials being integrated in some instances. Thin film lithium niobate is a good example of that. But actually, I think possibly for that milestone, there might be an all-silicon solution. We've already produced a modulator that will go at 200 gigabaud, and 200 gigabaud implies you might be able to do 400 gigabit per second in a PAM4 format. So we haven't done that yet, and we've done that still in a Mach-Zehnder form of the modulators. And a lot of people are working on ring resonators also, which potentially are much lower energy, and we also are working in that area. So in simple terms, the performance these days of silicon modulators is completely unrecognizable from the days when we started this work. And as I said, we didn't really even anticipate it would be communications in the very early stages, or that quickly changed when demands sort of appeared. Yeah.
And we'll see how it evolves, and probably something unrecognizable in another 10 years, right?
Maybe.
Uh, Silicon photonics has become a key platform for scalable, high-performance optical systems. With data demands growing from things like AI, what role can this play in supporting optical communication?
Well, I mean, we've just discussed the evolution of communications for data centers, and co-packaged optics is playing a key part in that too. So this is really, putting it in very simple terms, this is where we integrate silicon photonics, transceivers, modulators, receivers into an electronics platform in a way that enables you to get more optical signals in and out, and it enables you to communicate really from the electronics at higher speeds via the optics. So that'll be a key strategy, and the primary candidate for integration in with electronics in co-packaged optics is, of course, silicon photonics. But actually, as I mentioned, the success of the technology means that it also is being regarded much more seriously for many aspects of the more general communications network within the infrastructures that exist already. And so I expect to see a significant evolution in the applications of those areas too.
Looking into some of your achievements, you're a founder of the LiDAR company Point Cloud. Talk to me about the evolution of 3D imaging and where this field could be heading.
Yeah, so this is one of the interesting emerging applications, I would say. And there are lots of opportunities. There are also lots of integrated LiDAR companies around actually at the moment too. Um, Not everybody does it the same way, and I think Point Cloud has a particularly unique way of doing that. Now, I suppose the most obvious application that's driven that is autonomous vehicles, and in particular self-driving cars. But the ones that have effectively been deployed so far do not have an integrated photonic solution. So you might have seen typically rotating mechanical LiDAR on top of cars and so on. But what silicon photonics will offer you in such an application is to put the LiDAR onto a tiny chip the size of your fingernail, and you'll probably need a few chips for your system, but these can be deployed discreetly around a vehicle, and in the different positioning and the performance and so on, you can position them such that you can get all sorts of coverage, both not just 360, but at different height levels and angles and so on. Because the chip itself is very small, very lightweight, and because it's optical, is pretty immune to noise in some environments. But of course, there is an electrical interface, so you do have to take some care. But actually, that's just one application. There are lots of imaging applications, and in some instances, those have already been deployed in things like facial recognition and so on. But because you can integrate such high performance into a very small silicon photonics chip, I think we can expect to see that the whole quality of the imaging improve, the distances involved improve, all the different platforms improve, all the different applications. An obvious one might be drones, and obviously very lightweight if you've got just a series of small chips, and so it goes on. And I think really the applications are more or less limited by what you can think of deploying it on. So lots of opportunities in this whole field, and I think Point Cloud are doing particularly well at the moment too.
Yeah, always exciting when the limitations are your imagination, right? So, I mean,
Indeed, yeah.
we're really tapping into anything. Um, Talking about your time as a professor at the University of Southampton, you have the opportunity to shape minds of the next generation of innovators and professionals in the optics and photonics field. What are some of the most important messages that you try to leave with your students?
Well, I think probably the most important message is about the opportunities available today. I mean, obviously there are many opportunities. Many messages that I could obviously give you that are important. But given how silicon photonics has evolved from essentially just a handful of us doing it in the early days to now essentially a mainstream technology that is employed and deployed all around the world. And especially with the emerging applications, it means that students have the opportunity to either work in a field that really inspires and interests them, make a difference in that field, change the world, if you will, or maybe start their own company, develop their own technology, become a technology leader themselves. In many ways, I envy them. Back in the day when I started doing this, it was pretty difficult. People were not very accepting of a new technology. Funding was difficult. The world's changed enormously, so the opportunities are there. And what's more, the technology, has proven itself to be both reliable and commercially successful. So even if I limit myself purely to silicon photonics, the opportunities are enormous. But I could talk to you, more widely about photonics in general. In my role as director of the ORC at Southampton, I see some of our people doing amazing things. You may be familiar with a startup from Southampton called Luminicity, which was acquired by Microsoft recently. That's just one example of another new technology that was produced at Southampton. But Southampton has a long and distinguished track record in producing all sorts of photonics innovations long before I was here. And so photonics in general is so buoyant. Silicon photonics in particular is extremely buoyant, and the opportunities that exist for students, as to use your own words, are limited by their imaginations in many ways.
And we hear too, how fast photonics is growing, and sometimes it seems like maybe faster than employment can keep up. Do you think is there a gap in bringing in workers, or is there something we need to do to kind of just alert students and young professionals that there's a great opportunity here that you just may not have considered?
Yeah, I think all of the above, really. I mean, there is no doubt that. I mean, most people in technology in general would say there is a lack of trained staff at all levels, not necessarily just PhD level, but from technical support, technicians, and the whole gamut of professionals through the system. There is really a shortage of skilled people. So, I mean, I think it is an opportunity for both companies and universities to work more closely, to provide the training that people need, to provide, perhaps more focused levels of training that individual companies are looking for. But I think fundamentally we have to go back to a much earlier stage. I think, just notifying graduates of the opportunities, well, their ideas may be too well formed by then. There are lots of discussions surrounding how we influence school kids about how to get into technology. And I think they're obviously very influenced by their teachers, their schools, even the flavor of success that's gone with the school before. So I think if we can do more outreach, get into schools, get people at an earlier age, point out the fascination and excitement you get from working in an area of technology like this that perhaps you don't necessarily get in other avenues of employment. So I think there's still plenty to do, but it's a difficult ask. It's not the simplest thing to do to get into to persuade children about a particular technology or even technology in general. So I think, we need to work more closely with government in doing those types of things. And it isn't just something for the UK or, say, the US. I mean, all of my colleagues from around the world report a similar problem. And so, it becomes when we get to the point that we're in, and a technology like silicon photonics takes off, it does mean that there are a shortage of people and retention is difficult. Industry are snapping up people and potentially can pay them a lot more than perhaps universities can. But equally, universities are the breeding ground for the future generations of leaders. And so we need both strong universities and strong industry. So I think we need to essentially work more closely on this problem.
Yeah, yeah, certainly with I think there might not be an awareness for someone who's not thinking about what's around them that you are just surrounded by photonics, right? And people are
Yeah.
using their phone, their computer, their TV, they're driving their smart cars and maybe not aware of it. So just an exposure for a young child to be like, well, let me give you a little bit of an idea. And if you just get 1% of this, then maybe this can spark some interest.
Yeah, and photonics is known within our community as an enabling technology. And it's known for that reason because it's often not visible, as you quite rightly say. If someone's doing facial recognition on their phone, they probably don't realize that photonics is involved. If they're calling another country, whether it's by phone or via their computer, they probably don't realize photonics is involved. If they're even just using the internet to do some sort of search, they probably don't recognize that photonics is involved if they're not part of the community.
Yeah. And then before I let you go, I want to ask you one question. It's going to be a broad one that may be impossible to answer because it requires a little bit of seeing into the future. But we talked about the applications, but what is really the limit or the future for silicon photonics? And are there some hurdles or maybe bottlenecks that are kind of currently keeping it from reaching the next level?
Yeah, I would say there are, and I think for a more established application like the communications that we discussed, there is a need for standardization. There's a need for modeling that translates more readily to manufacturing. So, for example, if you wanted to make an electronic circuit in an electronics foundry, and you use their models to work out the performance of your circuit, essentially, if you can get it to work in their models, you'll get it to work in real life because the models map so closely to what is actually fabricated. Photonics is not there yet in that regard, and so it's not quite as easy for a fabless company, let's say, to produce a circuit that's readily going to work because that mapping doesn't translate automatically. And that's why at this point in time, prototyping is so important, in order to develop that roadmap. So there's a couple of things, but that's really just in the established applications. I think there will be requirements in other areas too. I mentioned already the requirement for different waveguiding platforms for different wavelengths in application areas. A good example of that is healthcare, where you quite often are interested in longer wavelengths to map into what's called the fingerprint region, because specific drugs or chemicals have characteristic absorptions, and those absorptions are strongest in sort of longer wavelengths, even though there are sometimes corresponding absorptions in the shorter wavelengths. But if you want to, therefore, take advantage of those stronger absorptions, you need a platform that is operating in those longer wavelengths. Now, it can still be what would come under the umbrella of silicon photonics, and essentially silicon-based or related compounds, and therefore you'd get all the benefits of silicon photonics. But those platforms are not well established so far. Although Cornerstone does offer some of those as a way of getting into that process. And the same applies, I think, for many of the other applications. Because they're so much earlier, standardization is the last thing on people's minds, really. They're more trying to develop the technology, but standardization will be required. And I think, there is an element that you have to be careful it doesn't come too soon, because you wouldn't want to rule out some areas of technology because you've standardized on this platforms say. But nevertheless, if you look at sort of successful manufacturing in the main, standards are vital, and so standards are required. It's just a case of getting that in the right time of the development. But I think the other thing that will be needed. So if we take the communications, I mentioned the aim of 400 gigabit per second on a single channel. Well, what about after that? There will need to be innovations in the technology. History tells you that once we reach a certain speed, we always want more. There is an energy demand that goes alongside that. We've got to produce better efficiency and lower energy and so on for the communications applications. And the same will be true. There will be some other critical parameters for the emerging applications, not just in terms of standards, but in terms of innovations that are required to move the technology along. Now, fortunately, I think that's why universities are important. And it's particularly important for smaller companies who can't afford their own research activities, their own research environments to work with the universities. But even for the larger companies, a lot of the critical innovations have come out of the universities. So it's that same conclusion you come to, that industry needs to work more closely with the universities, that we came to on the training applications in order to develop technologies. So you can probably tell from my rather long answer that I could talk about this for some time. So maybe I'll stop there and leave it at that for now.
No, I appreciate the insight, Professor Reed. Thank you so much for joining us and sharing your thoughts on this. And we look forward to seeing what Cornerstone can do for the silicon photonics industry, and can do it to advance its place, the UK.
Thank you so much. Me too, by the way.